Hello and welcome to another video brought to you by the AI team at Samsung SDS. My name is Patrick, and I'll take you through a presentation of the data science workflow, which are the steps that a data scientist typically goes through in order to generate a new piece of AI and to deploy it in the field. It's a 7-step process, of which the 5 middle steps are the actual data science. The first and the last step are pieces of communication that need to be performed to first of all discover what the challenge is that we're solving, and at the end perform the change management needed to get the end users to adopt the new technology to solve that problem. I will focus on those 2 communicative steps in a separate video, and for today focus on the middle 5 steps of actually doing the data science. The first step is data acquisition, where we actually record, gather, somehow obtain the data that we need to train our models. Of course, the data set that we initially get is raw, and it needs to be cleaned, by which bad data, outlier data, statistically irrepresentative data are removed from the data set, and the data set hopefully is then statistically significant in the situation and representative of the problem that we're trying to model here. And so at the end of the data acquisition stage, we hopefully have a clean data set that actually represents the situation. Next, we typically have to label the data set, which is a point where human experts or domain experts are inserting their human knowledge into the data set. This is most often needed in the case of images, where we might have to say, okay, this image contains a person or a dog or something like that, or we have to write a bounding box around a certain part of the image. Next is the feature selection stage, where we have to either generate new features or select the right features of the data set that are going to contain the information that we want to learn. Typically speaking, data sets will contain features that are not very expressive with regard to the problem that we're trying to solve, and so those features have to be removed. The features that do have lots of information need to come to the forefront. Next, we want to select which type of model are we going to use. Is it going to be a neural network or a decision tree or a support vector machine or something else? That needs to be chosen. And the parameters of the algorithm that generates that type of model need to be tuned. There are choices that you can make, and you need to make the right one. Having done all this, you then actually perform the training for the model that you've chosen, and then you can deploy the model at inference. That is to say, you can use it in a real-life scenario post-training. So, having talked about what the steps are, 80% of the frustration in a data science project happens at the very beginning, because you might define the problem incorrectly or too vaguely, and then in the middle of doing the data science discover that you're actually solving a problem nobody had, and that the real problem is not being addressed. So being very precise and investigating in detail what the problem actually is very helpful in the beginning. 80% of the project risk happens at the change management level at the very end, by the very fact that often the end users do not adopt the AI that you've so laboriously developed. And so doing change management properly and early enough in the process is essential to getting the users to actually adopt it. Now, 80% of the work in terms of person hours is in the data stages, both the acquisition of data as well as the labeling of data. So here we're talking about the major sink of effort that we're going to look into improving. And the time delay happens at the 3 modeling stages, where the time is usually taken not by people but by computers. So that gives you a rough idea of where the risks and the budgetary items go in the workflow of data science. So we're going to look at reducing the workload and the delay by using certain technologies to help us out. Let's look first of all at the technology called active learning, where the idea is that we need to label the data, and that is a piece of activity that human beings perform. So in this case, for example, I want to isolate where in the image are the sheep. I might draw a bounding box around the collection of the sheep or around each individual sheep, or I might have to draw a free-form contour that gives me the outline of the sheep. Doing those activities takes time for a person, and to provide an AI with a good data set, you might have to go through this procedure for a very large number of images. On the right-hand side, you see an X-ray image of a person's lung, where again you had to label where on the image is the disease, in this case COVID-19, located, and you want to detect that using AI. So you see, doing this is a time-consuming activity. Now, the order in which you perform labeling is usually arbitrary. However, the order does matter. For example, if you have two images that are very similar to each other, the first one that you label gives a lot of new information to the system. The second one provides hardly any new information. And so you don't really need to label it anymore. But for large data sets that include hundreds of thousands of images, for example, you cannot track that in your mind anymore, and you would like the order of images to be established by the training system. And this is where active learning comes in. The idea is this: you have a large collection of images, but you're going to label only a very few of them at the beginning. You provide those labels to the computer, have it investigate on the basis of that what it can learn, and provide the confusion that it has about the rest of the images. It then provides the images that it's most confused about to you. You label them and you hand it back to the computer. Again, it gives you the ones it's most confused about. And you have this process of handing back and forth some labels and getting back some images that it's confused about. Now you do this 1% of the data set at a time, and eventually you come to the point where the computer is no longer confused about the rest of the data set, and it has enough information to train the model about the entire data set. In one particular instance where we were looking at X-ray images of people's lungs and detecting COVID-19 versus a healthy lung or versus pneumonia, we found out that by doing active learning, the model achieved its maximum accuracy after only 16% of the images were manually labeled. The other 84% of images did not need to be manually labeled because the computer had enough information after 16%. The other images simply didn't add information anymore. They added data, they added work, but they didn't add information to the detecting system. And so you can see that the amount of human labor that you can save by doing active learning is dramatic. In this case, we reduced it from 100% down to 16%. We saved 84% of person hours to train the system. Now, going to the actual modeling stages, we usually need to perform feature selection, which is choosing features that are already present, as well as feature engineering, which is generating new features that are not yet in the data set. This is typically also a manual activity that domain experts perform, and it's a trial and error process that can be quite time consuming. But there are ways of doing this algorithmically by which you automate the process. It becomes fast, it becomes fast, and it doesn't consume any human hours. So one example of doing this for images is to take parts of the image and call them features. So you see, for example, here down at the left bottom, we have an image of a dog. Now we take parts of the image, for example, the dog's head or the dog's legs, and we call those features of the image. Those were automatically selected, and then the model can learn that parts of a dog's body indicate that there is a dog in the photo, and it can then learn these things. By doing it in a way like this, we can automate the feature engineering process and learn those features that are most important about a particular class. Moving on to the model selection and hyperparameter tuning parts. Model selection is basically a question: which one of many possible models is the best one for my dataset? This is a trial and error process by which we select a model, try it out, assess it, and try out some more, and take basically the best one. Now, this is a laborious process for people to go through, but it can be automated, of course. Same with the hyperparameters. There are typically many hyperparameters that we need to look at and tune for a training algorithm. Some of them, like the learning rate, for example, might not even be constants, but might change over the epochs of training, so that these aren't numbers, but they are time series that we need to tune to the particular training task. And that too is a trial and error problem that typically people solve by trying something, thinking about it for a little bit, trying something else, and eventually coming to what they think is a good answer. Now, when you search for the best value of a parameter, what people often do is perform a grid search. So they search between a small value and a large value, a few values in between, and they might invest effort in these steps, both for parameters that turn out to be important and parameters that turn out not to be important, because a priori you simply don't know which of the parameters are in fact important and which ones are not. So the way to do this is to use not a grid search, but an adaptive search, to work smart, not hard. And so in an adaptive search, you pick a point and assess the model at that point and go on for a few more, but then you can, based on those results, interpolate and target those parts of the space of parameters that offer the best value. And in this way, as you can see on these images, you actually find the bottommost point in the space and find the best parameter value for the important and the unimportant parameters both. In the end, you then get the hyperparameters that you need to get the best performance, and you've done this automatically. Now, trial and error is usually expensive because each trial takes a certain amount of time. And therefore, usually speaking, AI training takes hours or days or even weeks of training, and trial and error on such systems then takes an unrealistic amount of time. So with bigger models or bigger data sets, doing trial and error processing to perform hyperparameter tuning or model selection is just simply unrealistic. So what people do is they try a couple of different varieties, pick the best one, and call it done. There is room for improvement left over, but we just don't have the time to do it. This is where distributed training comes in. In distributed training, you use a multitude of computers to do a single task. However, this usually requires a lot of engineering, IT engineering, by which you put together these various computers in a cluster. You install software packages such as Kubernetes or Docker to make them work together. You have to work with your AI frameworks to put them on there. And we discover that usually it takes a team of IT and data scientist folks many weeks to put together a cluster of computers like this that can actually work a single IT task. And this is very laborious, of course, because we typically don't have the staff to do this. Now, setting up a cluster like this is very laborious, and we don't really want to do that every time. We want to focus on doing data science rather than focus on doing lots of IT work. So what we really want to do is automate this entire setup process and simply say, I want to use 64 GPUs to perform this task. And that is possible. There are software programs out there, the Brightix AI Accelerator being one of them, that will accomplish that task for you, and you can simply execute your AI training task on a network of computers and get your jobs done quickly. So you would choose the language that you want to code your AI in, TensorFlow, PyTorch, Keras, whatever it is. You don't have to worry about the computing infrastructure at all, and you simply run your script. Ordinarily, you do this on your desktop computer. Brightix AI Accelerator allows you to do that in the exact same manner on a cluster of many, many GPUs, however many you want to use, and to execute that script, see the result, and be done. The benefit of doing that is that you get to do things a lot faster than before. Now, there's the high school problem. If it takes one builder 100 hours to build a house, how long will it take 100 builders to do that? The answer they're looking for is 1 hour, right? It's a linear scaling issue, even though in real life, these builders would have to communicate with each other a great deal and lose time. So it won't be 1 hour. In the case of computers, the same thing applies. Each computer gets a part of the task and they have to communicate with each other, so the network speed has to be high. But nonetheless, we discover in real life that because each of the GPUs has a memory available on it, that memory that you gain in total actually allows you to speed up the training even further. And so we come up with the observation, this is a practical observation that we see in real life, that using more resources actually accelerates the training. So in this case, we trained a Distilbert model using 64 GPUs, and we found out that if we increase the number of GPUs from 1 to 8, so an 8 times increase in resources, we increase the speed by 14 times. Now, that's superlinear scaling, right? It's not just reducing the time by 8, it's reducing the time by 14. And that is because we have this extra memory available. So distributed training reduces the amount of GPU hours and therefore actually saves you money on hardware and electricity costs, and gets the training done in a small fraction of the time, allowing you to then perform the trial and error tasks that you couldn't perform beforehand. So distributed training becomes not only a cost and effort saver, but it becomes an enabler to do AutoML, to do automated feature engineering, model selection, hyperparameter tuning, and eventually, of course, get you to a more accurate model. And this is how we can save workload in the data parts of the workflow and save project duration in the modeling part of the workflow, and overall make your project a lot shorter, a lot cheaper, and the result a lot more accurate. Brightix AI Accelerator is the software that enables all of these things, distributed computing as well as all the AutoML features and the active learning that I've talked about. And we enable this for you with our partners. The software runs on Amazon Web Services, it uses NVIDIA GPUs, we use NetApp storage systems, and we're capable of exporting the models that we've trained to FPGAs to be able to run on the edge using the Mipsology software. Thank you very much for your attention, and feel free to contact us for more information. If you would like to try Brightix AI Accelerator, please go to our webpage, trialaccelerator.ai, to run a free trial and see what we have to offer. Please like the video and subscribe to our channel down below I look forward to seeing you again on future videos. Thank you very much. Bye-bye.